All right, so now we're discussing stoichiometry. This is relating, understanding stoichiometry, understanding the basic processes is very critical in analyzing and getting useful work out of balanced chemical equations and a lot of chemical processes. So let's look at what stoichiometry actually is. I think a good way to visualize it is, how we look at carbon through the carbon cycle. And this is in our environment. Carbon goes through the cycle through our atmosphere as CO2. Plants in it, take in CO2, they store this in chemical energy, using chemical energy from the sun, I should say, and produce saccharides, sugar molecules. We take in sugar as energy. We exhale CO2. Dead plants, animals, animal waste, that goes back into the environment as carbon, which eventually results in CO2 being released in various techniques, or actually being buried, forming fossils, fossil fuels, things like that. And tracking carbon through this carbon cycle is kind of difficult because there's all these different reactions involved in respiration, photosynthesis, digestion, decomposition, metabolism. And these reactions, though, don't care about masses of carbon. They care about numbers of molecules, numbers of atoms, but we can't count numbers of atoms. As we discussed, we can measure mass, so measure masses of carbon present as CO2. We measure masses present in our bodies, masses present as sugars and saccharides and polysaccharides in plants and animals. So we need to relate these two. We need to relate what we measure in the labs as mass to the chemical reactions themselves. We've already discussed we can use the periodic table to relate mass to moles of a given compound. Now we need to relate moles of one compound to moles of other compounds to better analyze chemical reactions. So, for example, in photosynthesis, we have the simplified version of the process. As we discussed with combustion, CO2 and water really have very little chemical potential energy. They're fairly stable molecules, very little energy stored. Plants take CO2 from the air and water from the air or from the ground and convert this into sugar and oxygen. Sugar and oxygen, this is one type of sugar they produce, glucose, and oxygen have stored chemical energy. The way plants do this is they take energy from the sun and they really store it in these new molecules. So it's kind of like nature's version of a battery, nature's version of storing solar energy in these chemical structures. Respiration, really the reverse of photosynthesis. The simplified version of what our bodies do is our bodies take the sugars that we eat, we ingest, all the foods, we inhale oxygen. Our bodies use this to produce CO2 plus water plus energy that our bodies need for metabolism, for even keeping our bodies warm, for all the chemical processes come from this reaction. Really very similar to the combustion process. Combustion, we have a fuel, in this case such as a sugar, plus oxygen, produces CO2 plus water, plus energy as heat or light. So it's a similar net process, but the steps are, of course, a bit different inside of our bodies. So when we look at these chemical reactions, let me get rid of some of that ink there. Let's compare the coefficients and what they mean. So in this reaction, we have a coefficient of 1 in front of the CO2, 1 in front of the glucose, and 6 is in front of water and oxygen. These coefficients tell us ratios of one compound to another in this balanced reaction. What this says is that for every one carbon dioxide molecule, I need to have 6 water molecules to react. For every one CO2, I'll produce 1 glucose molecule. For every CO2 molecule, I'll produce 6 oxygen molecules. So this is what the coefficients tell us. They do not tell us how much of any of these things we have. It just gives us ratios of one to the other. And we use this to compare the different components of chemical reactions. This is really what stoichiometry is. Again, these coefficients only relate numbers to numbers. Number of molecules to number of molecules, or moles of molecules to moles of molecules. So, as I said, the coefficients of a balanced equation relate numbers of any compound to numbers of any other compound in that reaction, or element. It really could be elements or individual elements or compounds. And when they relate numbers, moles are just measures of numbers, so we also relate moles to moles by the same ratios. These ratios are used to effectively convert between any two compounds or elements, or pure elements, I should state, in a given reaction. Doesn't matter if they are reactants or products, we can relate anything that has a coefficient in front of it. And so this allows us to calculate moles of reactants that we need, moles of products that should be produced. In more advanced chemistry, we can predict the amount of energy that's needed to get a reaction to start, or how much energy it's going to produce. So we get a lot of information from better understandings of these balanced chemical equations. So for example, the reaction between potassium and sulfur to form potassium sulfide, we balance it. 2 Ks plus 1 S forms K2S. It always helps, I think, to visualize what's happening here, especially when we start discussing later in the chapter limiting reactants. It helps you understand the process so it makes more sense, because too many students try just to memorize, I go through this step, this step, this step to do this calculation or to figure out limiting reactants. If you understand it, it becomes much simpler, and you can also catch any errors that it's easy to make. So in this case, on the right side, we show that we have 2 potassium atoms plus 1 sulfur. That's what our coefficients are telling us. And when they react, they produce 1 potassium sulfide, and our reactants are gone if we have the right numbers. By the same token, we can also react 2 moles of potassium with 2 moles of sulfur to produce, 2 moles of potassium with 1 mole of sulfur, and we'll produce 1 mole of potassium sulfide. So it's the same ratio whether we look at atoms to atoms or moles of atoms to moles of atoms. It'll be the same process. So in order to perform a stoichiometric calculation, several steps we need to go through. First, of course, is to write a properly balanced chemical equation. So write down your proper chemical formulas first, reactants on the left, products on the right. Once you write the formulas down, again, do not change the subscripts. Figure out your proper coefficients, lowest whole number ratios. And these whole number ratios, the whole numbers, are the ones we're using for our calculations, for our stoichiometry. There are lots of shortcuts. The text goes through some, tutors go through some teachers tell you some, especially for the first year or two of chemistry. I suggest to avoid most of these shortcuts. They can lead to confusion. Once you understand the process better, it'll make more sense to you, but trying to memorize shortcuts really is not a good idea at this stage. So again, coefficients relate numbers to numbers. They relate moles to moles, same thing. So always convert what you're given to moles, do your calculations, and at the end convert moles back to whatever you need to. So if you're given concentrations or volume or mass, whatever you're given, convert that to moles first, because that's what stoichiometry needs. We need to have moles. And at the end, make sure you're answering the question asked. So once we have the moles, we use the given amount of moles and the molar ratios to figure out what we need. As with any other conversion factor we've done this semester, make sure that your original unit cancels out. Make sure that your desired unit is what you're ending up with. So again, write your units out. Just a good way to make sure you're going through the right process. And at the end, you'll get moles for your answer. And then if you need to, convert moles to something else. You might need to go moles back to mass, or moles to concentration, moles to liters. But you always have to go through moles. It's just a good rule of thumb. Again, avoid the shortcuts that people try to tell you. It's just much safer to use the same thing every time. It might be an extra step or two in some cases, but in the long run, it'll help you out quite a bit, help you understand the process better. And this is an example. I'm not going to go through this one. I'll go through in the next video, just break this up into 2 videos, some example problems for you to work out. One problem here is I do want to point out how much CO2 enters the atmosphere from the combustion of so many kilograms of carbon. This is a bit more complex. I want to start with just doing mole to mole conversions first, then worry about mass to mole conversions. But when it says how much, it actually doesn't state in what units. So if I do this on an exam or quizzes or things, ask me, let me know what I mean, because that's very open-ended. I could answer this in moles, I could answer it in grams, I could answer it in kilograms or some other quantity, or just exact numbers of molecules of CO2. They're converting to mass at the end. And even the way they do some of these conversions I don't like, because really this should say grams of carbon to be proper, kilograms of carbon, grams of carbon. Over here, kilograms of CO2 is what they're trying to get to. Grams of CO2 down here. And this is where, while we try to stress, put in all of your units, use proper units, because sometimes you'll get grams of carbon and grams of CO2. If you for some reason forget to do the conversions in the middle, you skip a step somewhere and you don't pay attention to the units, you get things canceling out, but grams of carbon don't cancel out grams of CO2. Those are different grams. So The book is a bit lax about this, and I think this is uh, not a good habit. So make sure when you write down even masses, include the mass of what you're talking about. Again, it really helps you quite a bit, helps minimize mistakes. And whenever you get done with the problem, especially on exams, you can go back and double check your work much more easily if you include all of your units, because otherwise you have to assume I meant this or that or whatever it was, and it's just a much better habit for you to get into.